All right, so if you've taken any biology classes, most of you are familiar with the basic biochemistry of carbohydrates. This is how chemists normally think of carbohydrates in terms of biology. We remember that if you have 6 equivalents of carbon dioxide and water, and you have a bunch of sunlight, and you've got a plant that can do photosynthesis or bacteria that can do photosynthesis, really you can convert this into glucose, right? What's the purpose of making glucose from a biological standpoint? Energy storage, right? Really, if we think about this, it's a really unique way of storing hydrogen at a molecular level. So we're going to reduce that CO2, and we're going to store a bunch of energy in the bonds of these carbohydrates, at which point we can perform aerobic oxidation and get that energy back out. We're not going to go into the biochemistry. However, I did want to introduce the main classes of carbohydrates from an organic point of view. There are 2 main classes. The first one, and I'm going to start using Fischer projections again. I know. Is where you have an aldehyde on the top. And I'm just going to pick some example ones. I've got OH, OH, OH. And hydrogen's over here. This class is called an aldose, simply because of this aldehyde. The other class is similar. However, instead of an aldehyde, we have a ketone. So I'll come through, put a ketone on here, and an OH. CH2OH. Then we've got 3 hydroxyl groups and 3 hydrogens. These are called ketoses, simply because we're dealing with a ketone, not an aldehyde. What I gave you guys up at the front is a family tree of all of the carbohydrates, but I want you guys to help me identify these 2 different carbohydrates. So on one page, I gave you a family tree of ketoses, and on the other side of the page, it's got a family tree of aldoses. What's the one on the left going to be called? Anybody want to help me out? What was it? Yeah, D-ribose. So if we look on the one on the left, we've got a D-ribose. Just one second. What about the one on the right? So the one on the left is D-ribose. Yeah, we've got D... I'm not even sure if I'm pronouncing this right. D-cyclose. We can also identify these as generic carbohydrate classes. If we look at this one, we've got a backbone that's 1, 2, 3, 4, 5 carbon long. This would also be identified as an aldopentose. An aldopentose is just any variant that has a 5 carbon backbone and an aldehyde head. If we look at the one on the right, it also has a 5 carbon backbone. However, it's a ketose, so this would be a, oops, actually I forgot a carbon. For this one, the carbon starts up here, 2, 3, 4, 5, and 6, so this would be a ketohexose. The other interesting thing when we're looking at these is the position of one of the hydroxyl groups. If you look at all of the ones on the handout that I give you, the bottom right hydroxyl group is always to the left. You guys notice that on the family tree? I don't have any of them drawn to the right. This identifies these sugars as D sugars. So it's always going to be on the right side of the molecule. Nature is very, very particular about the stereochemistry at that specific carbon. So this specific carbon in nature always has that hydroxyl group pointing off to that one direction. The interesting thing, if you remember back to fall term, was I was talking about L-glucose. L-glucose is where you have that hydroxyl group actually on the other side. Does anybody remember what was unique about that? Trivia from first term? Yeah, so it'd be a diastereomer. The cool thing with L-glucose is it's not natural. Nature does not make it. It tastes just as sweet as normal sugar, but it is 0 calories. The problem is, because it's not natural, it costs like $100 a gram to make, and it's super inefficient if you want to come up with a low-calorie sweetener. So you can artificially make L sugars, however, the D sugars are the only ones that are made naturally. The L sugars are under a lot of investigation now due to their interesting properties. So let's think about this. If we think about all of the aldopentoses, how many natural stereoisomers would there be for aldopentoses? You can also use your sheet as a guide. So this is good review for the ACS. If we just look at this Fischer projection, how many stereocenters do we have? We've got 3 of them. So if we think about the 2n rule, that would be 2 to the 3, which would be 8. However, we know that one of those stereocenters is always defined in nature as being a D sugar. So if we think about this, there are 8 possible stereoisomers. But only 4 are natural. Same thing with the one on the right. Only 4 ketohexose stereoisomers are natural, but there are 8 possible different stereoisomers that you could theoretically make in a lab setting. Does that make sense? How many of you guys are a little rusty on Fischer projections? All right, I was wondering about that. So let's do a little bit of review of Fischer projections. Because carbohydrates oftentimes are drawn using Fischer projections. Let's do this example that we had right above. This was our D-ribose. If you remember, the Fischer projection example I gave you guys in fall term was the example of the cat on its back, right? And its legs are sticking out towards you. That means all of the horizontal substituents are going to be wedges. So let's redraw this a little bit. You can kind of make these bow ties. So you've got OH, OH, OH. You've got hydrogens here, and then you've got a CH2OH, and then you've got a carbon, an oxygen, and a hydrogen, right? What about the backbone? The vertical portion going up and down? It's going to be curved backwards, right? So if we think about this, the horizontal substituents are coming out towards you, the vertical backbone's curved away from you. So the vertical portion is curved back. So another way we could draw this would be to have this as a dash and kind of that as a dash, right? So it's kind of curved back into a C shape. Let's try to identify a stereocenter, because if we think about this carbon right here, it's a stereocenter, but is it an R or an S stereocenter? So let's try to identify one of these stereocenters. What would be highest priority? Oxygen, right? Because if we look here and here, we've got carbons and a hydrogen, so oxygen's a higher priority. What would be next highest priority, the top carbon or the bottom carbon? Top carbon. So we've got 2, we've got 3. So if we look at this, we're going counterclockwise around it. So will this be R or S? R. It'll be R. Why will it be R? Yeah, the lowest priority is pointing towards you. If the lowest priority is pointing towards you as a wedge, you got to flip that stereochemistry. So in this case, this would be an R stereocenter. So sometimes it is a little bit tricky, but just make sure you slow down and assign priorities correctly. Sometimes model kits will also help with this. So if you do need to break out a model kit and physically build these, that can help you manipulate them and rotate them around in three-dimensional space so it's easier to see. But we're going to be using Fischer projections a lot this chapter. Also, if you do want to pull up the old course notebook from fall term, it's still up online, so you can go back and review notes from that section as well.
So in determining the RMS for the center current?
Yep.
Since you haven't really specified which line is going, I guess they're both going away?
So you want to do the middle carbon?
Yeah.
All right, let's do that. This is good practice. All right, so now we're going to look at this carbon right there. That is also a stereocenter, right? It's got 4 different substituents. Highest priority is going to be this oxygen. Now the question is, what will the second highest priority be? Well, if we go 1 carbon out, we've got a tie, right? That carbon and that carbon, they're both carbons. So what we look at is this carbon is attached to an oxygen, a carbon, and a hydrogen, right? If we look at this one, that carbon is attached to an oxygen, carbon, and hydrogen, right? So we're at a tie. That means we need to go further down the chain. So I'm going to erase this. We'll go 1 more carbon down. Now if we look at this carbon versus this carbon's attached to 1 oxygen, a ghost oxygen, and then a hydrogen. Why do we have a ghost oxygen? A double bond. If we go down here, this carbon is attached to an oxygen, a hydrogen, and a hydrogen. That means the top one's going to be the higher priority, right? So we could go 1, 2, 3. So now we are going counterclockwise. Will this be R or S? R, because if we think about it, the hydrogen, again, is going to be a wedge going towards you, so we've got to flip that stereochemistry, and this will also be an R stereocenter. Yeah, so it is a little bit tricky, but if you need to, like I said, break out your model kit and kind of rotate it around in three-dimensional space. All right. So we talked a little bit about carbohydrates, I think back when we were working on pod 5. So do you guys remember that pod where I gave you guys D-glucose and I asked you to do the cyclization reaction? All right, see pod number 5 for a bit of review. It's also in the course notebook. But the general idea was that if you've got a molecule like this, and you treat this with catalytic acid, you've got one end that's a nucleophile, and over here you've got an electrophile. So anytime you've got a setup where you've got a nucleophile and an electrophile on the same parent molecule, they tend to cyclize, right? And if we look at this, we've got a chain that would be 1, 2, 3, 4, 5, 6. This means we would form a 6-membered ring. 6-membered rings we know are very stable. So if we were to go through and do the whole arrow pushing mechanism for this, you would end up with a compound that looks a lot like this, where you've got a hydrogen coming off here, and OH there, and this would be 1, 2, 3, 4, 5, 6, right? What's the functional group that we formed? What would this functional group be called? Oh, man. Yeah. An acetal is when you have two alcohols coming off. It can be a cyclic acetal or a hemiacetal. In this case, we don't have two alcohols. We've actually got a hydroxyl group coming off. I shouldn't say two alcohols. I should say two ether groups. In this case, we only have one, so this would be called a hemiacetal. And oftentimes sugars exist in this hemiacetal form, where they can interconvert between being in the ring open form or the ring closed form. The ring closed form is usually a hemiacetal, and the ring open form will be either that aldehyde or ketone form. So if you need to, go back to the pod section in the course notebook. So let's quickly look at it and just review this reaction so that you feel comfortable doing all of the proton transfers necessary in order to interconvert between the open chain form of D-glucose and the closed chain form. All right, so let's go back. And let's take a look at glucose. Glucose is the main carbohydrate that's talked about in biology classes. However, there's a bunch of other useful ones. Oops. And let's start out by drawing the Fischer projection. Actually, there we go. So we've got an aldehyde on the top, which means that glucose is an aldose. We've got hydroxide, hydrogen, hydroxide, hydroxide. Just like we said, D sugars always have that bottom hydroxide pointed to the right. And then we can fill in the rest here. So if we treat D-glucose with acid, it's usually going to favor the ring closed form. So this equilibrium is going to favor primarily the ring form. And if you guys remember in our pod, we can draw this ring closed form using chair conformations. So this would be chair number 1. So that was one conformation. The other conformation varies a little bit. Looks very similar for the most part. However, got a hydroxide there. What's the difference here? What do you guys think? Yeah, exactly. Somebody remembered it. If we look at this carbon right here, we flip the stereocenter. So technically, would these be enantiomers or diastereomers? Diastereomers, right? We flip one but not all stereocenters. This carbon is a very specific carbon. These are called anomeric carbons. So you can get either the alpha or beta position. Which one of these is going to be our alpha glucose? The one on the left or the one on the right? Left. So if we look at this, the alcohol coming off that anomeric carbon is axial. This means that this is alpha, right? If we look over here, this one's equatorial. which means that this is going to be beta D-glucose. So let's label these on the left and right. This would be alpha D-glucose. This would be beta D-glucose. And the only difference between them is that position at the anomeric carbon. And under acidic conditions, they can actually interconvert between alpha and beta. So these, if we look at them, are going to be called anomers, which are a special type of diastereomer. Meaning they only differ at the anomeric carbon position, not at any other positions. So that's one way of drawing D-glucose. Another way that you're probably familiar with in your biochemistry class is by drawing a Haworth projection. Oops. So what we're going to do is compare one of these chair conformations to the Haworth projection. Oops. We'll do beta D-glucose. You guys thought you got away from drawing hexagons and chair conformation again. So this is our chair. The Haworth projection is a little bit easier for a lot of biologists to draw, so you see it pretty commonly. It's kind of the side-on view of the ring. So these front bolded lines are the carbons pointed towards our eye. The back oxygen and carbon are kind of away. If we think about this, oftentimes you'll see it drawn with these pegs sticking straight up and down. Okay, if we think about this position right here, is that going to be sticking straight up and down, or will it be sticking underneath the ring? So we're trying to look at this substituent coming off the ring. So if we think about this carbon, it's labeled in red, right? It's right next to the oxygen. But we're trying to determine that CH2OH group. Is it going to be sticking up or down? Up, right? Because if we think about this hydrogen that's not really drawn in, whoops. This hydrogen that's not drawn in is sticking down, right? So let's finish drawing in our Haworth projection. We've got CH2OH sticking up. The hydrogen right here is sticking down. Whoops. Darn it. All right. Let's go over to this position. We've got an alcohol. Is that going to be sticking up or down in our Haworth projection? Down. So then we can go over here. We could do OH sticking down. Man, my pen does not like the new OneNote update. I apologize. So we've got an OH sticking down. All right, now if we look at this alcohol, is that going to be sticking up or down? Up, exactly. So if we look at it this time, the hydrogen coming off that position is going to be axial, so it will be sticking down. And then what about this OH group? It'll be sticking down, right? Because the hydrogen coming off that carbon is going to be sticking in the axial position straight up and down. So we'll do OH and H. All right, we've got one last position we've got to be concerned about, which is right here. Will that OH group be up or down? Up. And the hydrogen will be sticking down. So this is going to be our Haworth projection. And specifically, this is going to be the Haworth projection for alpha or beta D-glucose. Yeah, beta D-glucose. specifically because this OH group isn't in the axial position, it's kind of sticking in that equatorial position. So this is a Haworth for beta-D-glucose. It's a little bit different, but how many of you guys have seen this when they draw out nucleic acids and things like that? Yeah, it's pretty common with biology, so I do feel like I needed to show you guys this. It's not common for organic chemists, though. All right, there's a few definitions. I just want to make sure we get clear right off the bat. The first one is alpha, which means that the OH group coming off the anomeric carbon is axial. Beta, we said, means that the OH group coming off the anomeric carbon is equatorial. So we've got our definitions of those two anomeric positions. The other one that comes up, let's actually talk about anomers. They differ only in the stereochemistry. Of the anomeric position, or anomeric carbon. The other term that you'll often see is epimer. Epimers are closely related. They differ only in one stereocenter, but not the anomeric carbon. So you'll see anomers and epimers talked about in the chapter. The next one is mutorotation. Mutorotation is under equilibrium conditions. The ability to interconvert between anomers. Another way of thinking of this is you can have alpha go to beta, go to alpha, right? So that alpha D-glucose under equilibrium conditions can interconvert to beta D-glucose and then back again. So mutorotation is just describing that specific interconversion. All right, a couple more. There's pyranose and then furanose. What do you guys think pyranose means? Or furanose. How many of you guys remember from biology? I'll give you guys a hint too. If we think about furan, furan was one of our aromatic molecules, right? If you notice, furan has a 5-membered ring, right? So furanose is typically describing a 5-membered ring carbohydrate system. So whenever you see furanose rings, it's going to be a 5-membered ring with oxygen. Pyranose is going to be a 6-membered ring. with oxygen. Oftentimes you'll see carbohydrates that will exist as a 5-membered ring or a 6-membered ring. It really depends on the carbohydrate. However, we know that 5-membered rings and 6-membered rings tend to be the most stable ring sizes, and that's why nature does a good job of selecting them. Does that make sense? Okay. I know it's a lot of definitions, but it's kind of creeping in on biology, so I wanted to make sure we had those clear. All right, so let's talk a little bit about reactivity. We won't get very far into it today. First thing I want to talk about is reactions of monosaccharides, meaning one sugar molecule, not a sugar polymer. First one's pretty straightforward. It's acylation. So let's say I've got a molecule of D-glucose, specifically beta D-glucose. Let's draw it out. And we decide that we're going to treat this with acetic anhydride. We're going to treat it with a lot of acetic anhydride. What do you think is going to happen? Anyone? Anyone? Bueller? Yeah, it's going to form an ester, right? So going back to the carboxylic acid chapter, we've got a bunch of alcohols. We've got an acetic anhydride or an anhydride. Anytime you treat an alcohol with an anhydride, you're going to form an ester. Oftentimes what biochemists and organic chemists will do is they'll abbreviate this group as AC, which is short for acyl. And what this will do is react at every single position where there's an alcohol. So we'll just abbreviate this OAC, 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 and then OAC. So acylation can occur at any one of those alcohol positions. If you really want to dive down the rabbit hole, there are selective conditions for exclusively reacting at one of those alcohol positions, but you could spend probably a 6 months time frame learning about all of those reactions. We're not even going to go into that. Some crazy chemistry. The next one is alkylation. So let's say, again, we're going to use D-glucose. And I'm going to treat this with methyl iodide and excess. What do you think will happen with this? I should make my eye clearer. Yeah, we're going to make a bunch of ethers off of this. So if we look at the product from this, every one of those oxygens will act as a nucleophile, at least every one of the alcohols will. So we'll get methoxy groups coming off. However, oops, should be a methoxy group. However, we're missing a base, right? If we think about each one of these protons, we've got to get rid of them somehow. We actually don't want to use sodium hydroxide, because sodium hydroxide will do some weird chemistry that we'll see shortly. We need to choose a much more gentle base to help with the deprotonation. And we just saw one last chapter. We use silver oxide, specifically silver 1 oxide. And silver 1 oxide in this case is a gentle base. You cannot use hydroxide directly. And we'll talk about that shortly. All right. There's one more reaction I wanted to end on today, and this involves formation of what's called a glycoside. All right, with the glycoside, you don't react at all of the alcohols. You only react at the alcohol coming off the anomeric carbon. And anytime you have an alcohol coming off of this anomeric carbon, so this red carbon right here, it's called a reducing sugar. So let's make a note of this. If you've got an alcohol coming off that anomeric carbon, the sugar is referred to as a reducing sugar. With glycoside formation, what will happen is you treat this with acid and another alcohol. So I'm just going to have a generic alcohol. The first step is we're going to protonate this position. Oops, let me clean this up. I haven't done cyclohexanes in a while. Okay, so now we've got our protonated alcohol. Let's fill in the rest really quick. The cool thing with this is that the lone pair can actually clamp down and kick this off, right? So we're actually going to go through an intermediate that we're pretty familiar with. Oop. This oxygen now has a positive charge. We've got OH, OH. But we've got alcohol floating around. And this alcohol can now attack back into that carbon and kick up electrons. Let me fill in the rest of these groups. And oftentimes when you see this, you'll see it drawn like that. What does that squiggly line mean? Yeah, it means it's racemic. That alcohol, when it attacks in, could be in that axial position or equatorial position. So oftentimes it'll mix up that stereocenter, and it won't quite be racemic. We're not going to get into that, but there's something called the anomeric effect that actually favors the axial position over the equatorial. But you will get a mixture of a little bit of both. And then in the last step, all you're going to do is deprotonate this, and you'll get your glycoside. All a glycoside is a reaction where you now, instead of having an OH, you've got some sort of other nucleophile that added in to the anomeric carbon. So a glycoside have a nucleophile that was added to the anomeric carbon. How many of you guys like to watch food shows? So if you ever watch food shows, they talk a lot about the Maillard reaction. Have you guys heard of that?
Oh, yeah.
It's the browning of meat. So like if you cook a steak, you get that nice crust. This is actually a formation of a glycoside, right? Because if you think about cooking something, you're heating it up, and you've got nucleophiles around in the form of amino acids. So those nitrogens on your amino acid can actually cross-link into the sugars, and that's something that occurs in the Maillard reaction or anytime you caramelize food. So it's a really important part of food chemistry and biochemistry is the ability for nucleophiles to add into the anomeric carbon of sugars, whether it's a nitrogen nucleophile or an oxygen nucleophile. Either one can occur. If it's an oxygen nucleophile, then these are referred to as O-glycosides. And if it's a nitrogen nucleophile, it can be referred to as an N-glycoside. Those are the two possible options that are common in biochemistry. All right, I think that's where we're going to leave it off today. Tomorrow when we come back, we're going to talk about more reactions on the carbon backbone with carbohydrates.